Hello everyone. In this lesson we're going to talk about nuclear reactions and see what happens in them and how they're different than chemical reactions. So, quick review. A chemical reaction occurs when two atoms bond or break bonds and form new bonds. So down here we have this water molecule, and that's composed of an oxygen atom, that's this red guy, and two hydrogen atoms. They're bonded, that's what this little bar shows. They're stuck together, that's water. Here's a second water molecule. Now in a chemical reaction, those bonds break. So this bond that used to be here is gone, this bond that used to be here is gone, this bond is gone, this bond is gone, right? And now they're free to rearrange and make new bonds, and so two hydrogen atoms stick together, two hydrogen atoms stick together, and the two oxygen atoms stick together. Now you'll notice we started with 2 oxygen atoms, we ended with 2 oxygen atoms. We started with 4 hydrogen atoms, 1, 2, 3, 4. We ended with 4 hydrogen atoms. The type of element didn't change. The compounds did because the bonds changed, but the type of element didn't change. So in a chemical reaction, one atom's bonds are broken and then new bonds form, and we get a different compound, but the same elements make up that compound. Okay. Now, chemical reactions involve the valence electrons, it's the outer electrons, because that's what's bonding atoms together. So when we had oxygen, it's actually got its nucleus, and it's got its first two electrons, they're not valence, and then it's got its next 1, 2, 3, 4, 5, 6. These empty spots on the energy levels, that's where bonds are going to form. So a hydrogen atom actually has 1 valence electron. What happens is these two orbitals overlap, and so that 1 electron gets shared between two atoms. That 1 electron gets shared between two atoms. Okay? So the different bonds that atoms can make depend on their valence electron configuration, and when atoms form bonds, they usually are getting a stable electron configuration. Now, we model this, like I said, with spheres and sticks, and the sticks represent bonds, and when the chemical reaction changes, or when the chemical reaction occurs, the types of the bonds between the atoms change, but the number of atoms does not, and the type of atoms does not. Now, that bond actually has some energy stored in it, and that is because there is actually an attraction between the electrons out here and the nucleus here, and the atom also wants to get in a stable electron configuration, which means filling up its outer ring of electrons, getting to 8 valence electrons. And so that attractive force between the protons, the nucleus, and the electrons in the electron cloud actually leads to this idea that there's some energy, right? Just like if there's a rock on the top of a hill, it wants to roll down that hill because gravity's pulling on it. Well, if there's an electron on the outside of an atom, that atom is going to be attracted to a nucleus because there are protons over there, so opposite charges attract. Now, bonds are sort of like flat spots on the cliff, right, or the hill. You might get a rock that rolls down to here, and it could get to here, and it could stop. It's stable there. It's more stable than it was here. But if we can break that bond and get it over that little hump, we might be able to get it to even more stable, right? And so up here, it's got lots of chemical potential energy because it really wants to form a different bond. It's got a little less chemical potential energy. It's got into a more stable state. Little less chemical potential energy, more stable state, right? And so this energy is released or absorbed in a chemical reaction. It takes energy to break bonds, and then that energy is released when new bonds form. So we say energy is stored in chemical bonds. It's potential energy. And when the bonds are reforming, then that energy is released. And it can be released in a multitude of different ways. You might get heat, you might get light. So when you burn a candle, you're actually changing bonds. What happens is you have a carbon atom that's bonded to another carbon atom that's bonded to another carbon atom. It's a big long chain. That bond is about halfway down the hill, right? And so when you burn, what happens is the carbon bonds break, and then the carbon rehooks to oxygen atoms from the atmosphere, and that is a much more stable bond, so this thing is rolled down the hill. When we can't create or destroy energy, and so that chemical potential energy gets converted into heat and light when the candle burns. And so the potential energy that was stored in this carbon-carbon bond was converted to thermal energy as the reaction occurred. Nuclear reactions work in a very different way, and yet there's still forces that are going on that are affecting them. So a nuclear reaction occurs when the nucleus changes, right? Before we were just looking at electrons moving around. Now we're looking at the nucleus itself changing. And you'll notice I actually have polonium changing into lead and helium. This element is polonium. We ended with two different elements, neither of which are polonium. That's because the nuclear reaction involves the nucleus, and the nucleus has the protons, and the protons determine the identity, and so we can change the identity of an element with a nuclear reaction. Because it's involving the nucleus, we don't really show the electrons when we're doing a nuclear reaction. We show the nucleus before and the nucleus after. We're going to look at a couple different ways the nucleus can change in the next section. So, like I showed before, we had polonium. Polonium has 84 protons. After the reaction, the nuclear reaction occurs, we're left with lead, Pb, which has 82 protons, and helium, which has the other 2 protons, right? So this split apart into 2 different elements, and so the type of atoms change. The number of protons in these daughter elements is different than the number of protons in the element we started with. This also involves energy, but remember, the dominant force in the nucleus is not the electric force between the protons, it is the strong nuclear force, and the strong nuclear force is really, really, really strong. So the amount of energy that is either absorbed or released in a nuclear reaction is actually really, really, really big. Nuclear reactions release way more energy than chemical reactions. Nuclear power plants, right, can let 1 pound of uranium decay and get about the same amount of energy as 2 to 3 million pounds of coal. So the coal burning is a chemical reaction. The carbon in the coal is still carbon after it's been burned. Instead of being linked to a carbon atom, it's linked to an oxygen atom. It fell down that hill. The uranium changes into a different element in the nuclear reaction. So 2 completely different processes, but they're both changing one type of energy into another. And nuclear energy versus chemical potential energy, all energy can change form into any other form of energy. The difference is where it's stored, right? Chemical potential energy is stored in bonds, which is dependent on valence electrons. Nuclear reactions involve nuclear energy, which is stored in the nucleus, which depends on the strong nuclear force and protons and neutrons. So these show 4 different reactions occurring. They're already labeled. We've got chemical reactions up here, and we can tell they're chemical because they started with hydrogen, ended with hydrogen, started with oxygen, ended with oxygen. And these are balanced reactions, which are showing us this is actually 2 water molecules, so 4 atoms of hydrogen. This is 2 molecules of hydrogen, 4 atoms of hydrogen, so the amount of stuff didn't change. This is the reaction for photosynthesis. Carbon dioxide and water produce sugar, glucose, and oxygen. But again, carbon goes in, carbon comes out. Oxygen goes in, oxygen comes out. Hydrogen goes in, hydrogen comes out. So that's the arrow, right? In a chemical or a nuclear reaction, starting things are on the left side, ending things are on the right side. Thorium goes in, radium and helium come out. That's a nuclear reaction. We have an element we didn't have before. Hydrogen goes in, helium comes out. Again, nuclear reaction. We had an element we did not have before.